Hi. In this video on section 4.5, we're going to talk about power. So, some words to know would be power, and then the unit for power, which is the watt, and then another unit for surprisingly energy, the kilowatt hour. So, we should be familiar with these three words by the end of this lecture. Okay, so let's start talking about power and what it is. So, power is the rate at which work is done. So it's a way for us to try to be able to put into a time context how the energy of something is changing. Because we know that you can complete the same task, but completing it quickly can be very different than completing it very slowly. So that's what power is here to measure. It's here to try to make that change in energy a time independent quantity. Okay. So, what would we do to express that mathematically? So, we use a capital P for power. And if we just take the straight definition, we would, since it says that it is the rate at which work is done, we would just say that it must be work divided by change in time, right? Because the rate of something being done is always per time. Okay. Now, because we know that work is the same thing as a change in energy, we often also see power written as a change in energy per time. And that's how the College Board prefers to write it. So you will see that the equation for power is on the equation sheet. And they write it as a change in energy per change in time. Okay. But let's really talk about what this physically means. Okay, so what does it mean for something to be more powerful than something else? So, why don't we pretend like we're just lifting something up? So, if we have some kind of object, and let's say that that object has an FG, so it has a weight of 1 Newton, uh, we could lift that object up so that it is now perhaps something like 1 meter above where it starts. Now, we know that if we move an object 1 Newton over the distance of 1 meter, right? Then if we are taking a force then and moving it some distance, and so we would be creating a joule out of this. Well, here, hold on. This should really say change in energy because we have a Newton, we're multiplying it by a meter, we're getting a joule. So taking this 1 Newton object and lifting it up 1 meter has increased the energy of this thing by 1 joule. And we could do that very quickly, right? So maybe we take half a second to do that. We could do that very slowly. Maybe we take like 1 second to do that. And power is going to differentiate between those two things, right? So let's say our first time to do this was half a second. Um, and then the second time that we did it in 1 second. So the power in situation one would be 1 joule divided by 0.5 seconds. And 1 divided by 0.5 is 2 joules per second. For this second object, right, we lifted it up that same 1 joule. Sorry, we increased the energy of it by that same 1 joule. But this time we did it over the course of 1 second. So 1 divided by 1 is 1. So now we see, right, that doing things more quickly yields more power for us. If we do things more slowly, we're yielding a little bit less power. And you'll see that the units I wrote here were joules per second, right? Which kind of makes sense. Energy is measured in joules, time is measured in seconds. But this has a more common name. It is more commonly called the watt. Okay, so a joule per second is the same thing as capital W, which refers to watt. Capital W is a watt, named after, I believe he was also English, an English scientist. Okay, so I really should probably be writing capital W's at the end of this to show that these powers are being expressed as watts. Okay. Now, there is another way for us to talk about power, and this is kind of a underground way of talking about it. You will not see anything about this on the equation sheet, but it does turn out to be quite useful. What we're going to do is we are going to do a little bit of derivation here. We're going to say, hey, we know what power is. Power is work over time. Okay? Just getting it right from the definition. But we also know how we can calculate work, right? We can calculate work using the second definition for work, which is F d cosine theta. So we could also say that power is equal to F d cosine theta divided by time. And if I do that, you'll see hidden inside of that expression something very familiar. You may miss it at first, but it is there. It is some length divided by a time. And if we have a length divided by a time, you know what that is? Oh, yes. It is a velocity. So we could also try to calculate a power of something as long as we know the force applied to it, how quickly it is moving, and then whether or not those two are in the same dimension. Okay, we're using cosine of theta the same way that we use cosine of theta when we talked about work. It's a way to make sure that our force is in either the same direction as our velocity or our force is in the opposite direction of our velocity, but we are making sure that they are not perpendicular to each other. Okay, and this tends to be useful. It is absolutely not going to be on the equation sheet. Okay. Okay, let's do a quick example problem. So an Olympic weightlifter breaks a world record for clean and jerk by lifting 266 kilograms up 2 meters. And he did this in 2.2 seconds. So how powerful is our weightlifter? So you guys know me, I love a good picture. Here's this gigantic barbell, and here's our weightlifter. He's got his hands on it. He's ready to go. And the clean and jerk, you don't have to actually really know what a clean and jerk is in order to solve this problem. All I need you to know is that the barbell ends up above his head. Okay, so we started here. We ended here. Okay, and that barbell is 266 kilograms. We lifted it up 2 meters. So when we want to think about the power that how powerful the weightlifter is, we can think of that by thinking to ourselves, well, he has in fact changed the energy of this barbell in some way, shape, or form. He's done it by adding gravitational energy to this barbell, since he lifted this barbell up higher than it was before. So we could say that this power is the change in gravitational energy divided by the change in time. So we're talking about mg delta y divided by change in time. And we luckily know pretty much all these numbers. The M is 266 kilograms, kilometers, what was I thinking? Kilograms. G is 9.8 meters per second squared. He's lifting it up for 2 meters, and he is doing it in 2.2 seconds. So let's plug all of that into our calculator. 266 times 9.8 times 2, and divide that all by 2.2. And what we end up getting is that he is 2,300, and I'm just going to round this because it was like 2,369.8, which I am going to round to 2,370. That is how many watts of power that this weightlifter exerted. All right. Thanks very much.